We're going to take a look at section 7. Section 7 deals with transformations. What are transformations when you're talking about equations and graphs and stuff? Yeah, shifts, rotations, reflections, scale changes. Translations of slides, yeah, they covered that already. Okay, so we're going to start with the easiest of those, the shifts, the translations. Okay? So the idea here is for any of those default parent functions that we talked about yesterday, you can apply these rules to shift the graph around. Okay? If you're doing a vertical shift, you're going to affect the entirety of the function. In other words, what y is equal to. Okay? The nice thing about that is it behaves exactly how it shows. You're adding c means you're going up c. Subtracting c, down c. Okay? Horizontal, though, means you're going to affect the x directly, the independent variable directly. When you do that, it actually is going to behave in the opposite manner. Okay? So there, x minus c, you're going to go to the right, plus c, you're going to go to the left. Okay? I have a page at the very end that has all these on it we're going to look at, so I'll leave that up at the end. So don't worry if you didn't get it written down right now. And also, just in case I haven't been clear, because apparently I had a couple of students last period that were oblivious to this. These are up online, where it's like 6 of these slides per page. So this is up on there. You can print it off if you want. Anyway, for this part, given f of x is equal to x cubed, sketch h of x and g of x. So I'm actually going to do all these on the same graph. Okay, regular x cubed is going to look roughly. Now it says sketch, which means I don't need everything to be dead on for all the points. I just want a rough idea of what's going on. So this is the f function here. For the h of x function, how is that going to change? It's going to go up 5. So in other words, it's going to hit about here. And now's where I screw up the graph. Roughly like that. Not really, but close enough. That would be the h graph. What about for g of x?
It's going to go up 2 and right.
Yeah, it's going to go right 3 because it's inside the parentheses, so it's going to do the opposite. I'm still waiting for them to come through the wall at some point. Sorry. Right 3 and up 2. For you, not for Jordan. If they came through the wall, he said it'd be exciting. So, for this one, that's going to be where the point where it used to cross the origin. So now it's going to come up, go through that, and go down.
At least break the window.
Questions on that? Now, another type was that we talked about was reflection. Reflection, again, if it's affecting the entire function, it's going to be a vertical reflection. Now, a vertical reflection means it reflects over the x-axis. It reflects vertically. If the negative sign is inside the parentheses, inside the function, it's going to reflect over the y-axis. It's going to reflect horizontally. Okay? So, if I have y equals x to the 4th power, so a quartic, what would happen to the equation where this is just y equals x to the 4th in order to cause this? So default kind of flattened out parabola.
We're going to add 2.
You're going to add 2.
And we're going to negate it.
So I'm going to take the regular f of x function. Am I going to add 2 to the x or to the whole function?
The whole thing.
To the whole thing. And what am I going to negate? The x or the whole thing? Whole thing. So I'm going to put a negative here. So that's the kind of default with f of x. Now if I apply it to x to the 4th, the actual function here is g of x is equal to negative x to the 4th plus 2.
I agree.
Okay. Honestly with these though, especially when we get into some of the reflections and some of the stretching and shrinking stuff we'll do in a second, it doesn't hurt to plug into the calculator real quick and look at it, make sure it matches. Okay. For this one, how does h of x change compared to the original f of x?
They subtracted
Inside the
Subtract 3 inside, yep, inside of here, subtract 3,
negate the whole thing.
and negate the whole thing. Okay, so now when I translate that to the function that we're using, it's going to be negative and then parentheses x minus 3 to the 4th. Does that make sense? Okay. Next up, now my default isn't one of the regular parent functions. It's a modification. What would be the parent function of this thing? Just square root of x, yeah. So if I just graph regular old square root of x, what's that one going to look like? Yeah, it's that half parabola thing opening to the right. So what's this default function going to be then?
It's going to be 1 to the right.
1 to the right. Because it's inside of the function. In this case, the function is square root. So it's going to move 1 unit to the right and still look the same. Now, what's going to happen when I take that function and add a negative sign in front? Reflected over the x axis. It's on the outside, so it's a vertical reflection. It's over the entire thing. So it still hits at 1, 0, but now comes down and goes out to the right. What about this one compared to the original? So it's over the y-axis. So if I'm out here, I'm going to flip over to here and go off in this direction. Questions so far? Okay. Now, those are all types of what are called rigid transformations. In other words, they're not actually changing the shape at all, its size or shape. They're just moving it around. Okay? Non-rigid transformations are when they distort the graph. Okay? That's fine. I can tell it was about math. I'm not worried.
If you did like negative, like in front of the square root, and then did like negative x inside, would it like flip and then flip again?
Yes,
Okay.
it would.
Another question.
That's fine. You're paranoid. Actually, wasn't. I heard you were talking about math and I didn't care. For this, distortion-wise, it's going to stretch or shrink it either vertically or horizontally. Now, if you're outside of the function, okay, and you multiply by some number bigger than 1, it's going to stretch it vertically. Because the idea is, for any x value you go over, you're going to go over a multiple of that x value. So if it's a 5 out front, instead of going over 1, or if you went up 1 and over 3 before, now you're going to go over 1 up 15. The thing is, when you get to the horizontal one, the problem is x and y are connected. Okay, it's an axis, right? So imagine you had like a beach ball or something. Okay, if you push in on the sides, if you shrink it horizontally, what happens to it vertically? It gets bigger, it stretches. Same thing this way. If you crush it vertically, it's going to get wider. So that's why you actually get an opposite behavior here a little bit. Horizontal shrink is if this number inside is bigger than 1. Because if I multiply the input value, it's going to cause it to accelerate that much faster. So if I have 3 times the x here, okay, it's going to make it grow that much quicker. So it causes a vertical stretch but a vertical stretch is the same as a horizontal shrink. Okay. And if it's a fraction, it's the other one. For this, if I want to compare these two graphs to x squared, so your default parabola, right? If I have 4x squared, how would you describe the transformation? Vertical stretch by a factor of what? 4. So the vertical ones are usually fairly easy. What about the B there? Vertical shrink by 1/4. Okay, not too bad. Horizontal, if I have this function,
Horizontal.
that's what I said.
To the second one.
Okay, f of 2x. So, stretch or shrink for the first one?
Stretch.
It's going to be shrink. Because when you do the x, remember, it's pretty much always opposite, right?
So,
Because what ends up happening here, this is a horizontal shrink, by a factor of what? Yeah, it'd actually be 1/2. Because it is by a factor of 2 if you want to think about it, but you're dividing by 2, so times 1/2. Okay? Now, think about what happens when I put that in here. The reason this is going like this is when I put it in, that's going to be 2x, that quantity squared, right? Well, if I simplify that, that's what? What's 2x squared if you get rid of the parentheses? 4x squared, right? So the idea, by shrinking it by a factor of 1/2, that's the same thing as stretching it by a factor of 4, vertically. Because you're going to hit those x values that much quicker, is what's happening there. So instead of inputting, where I used to input 2 and get out 4 from the function, I'm now, every time I would have done that, now I'm actually putting in 4 and getting out 16. So it's increasing vertically 4 times as quick because I'm doubling the input value. So it's causing it to actually shrink this way because it's growing so much quicker vertically. Okay, that thing can be a little counterintuitive. All right, what would the next one be? Yeah, horizontal stretch
by 2.
by doubling or by a factor of 2. Yes.
So basically, vertical shrink and stretch, the factor is always the number it is, and then for horizontal, you switch it.
It's the reciprocal.
Yeah.
Yep. And honestly, a lot of times, just to avoid this, well, especially if it's just a simple polynomial like this, people will plug in the 2x and write out what it is. Because if you wrote vertical stretch by a factor of 4 after you did the simplification, I would take that. It's the same thing in the case of this problem. So you can describe that one either way.
Oh,
Well, we have to, on the test, we say like it moves left and right or up and down. Shrink and stretch.
Yeah.
Or will we just like draw it?
No, you'll have to be able to describe what the transformation is, yes. Okay. The thing is, you'll also be able to graph it on your calculator and use both images. If you're completely thrown, it takes longer, but you can do it. Any other questions? Okay. Lastly, I'm just going to put this up for those that want to get all those down in one spot. Otherwise, that's all I have for today.
easy lesson.
It's not too bad. Honestly,